like to introduce our first speaker, Dr. Jenny Zhou from Monash University. Dr. Zhou is actually a SIM coordinator of our CRC. She's in charge of the indoor environmental quality, which is really part of really what we are talking about today. She's also affiliated with the Monash Smart Manufacturing Hub and the Monash Energy Institute. Jenny has been at the forefront of providing occupant-centric and resource-responsive buildings. So her research has attracted a lot of attention from industry and government partners, such as CSIRO, the National Health and Medical Research Council, Austrian Co-Industry Research Program, USAI Energy, and many others. Great work. So over to you, Jenny.
Okay, thank you. Okay, today, I think later, so we are going to, Phil is going to talk about how to achieve the 7-star through the design. But the topic I'm going to cover today is a little bit, probably it is, what's the story after the design? So the keyword here is the building performance gap. So the performance gap, by definition, it is the discrepancy between the design prediction and the real life performance. A lot of the building rating system, including the NatHERS 7-star we just talked about, so they usually rely on the simulation to predict the energy efficiency and different performance indicators of a building. And also the simulation result is used to demonstrate the compliance with the building code and maybe other regulation instrument. However, so we just talked about the target about the carbon. So if in real life, we really want to harvest the carbon reduction from the energy efficient buildings, then we need to, make sure the energy efficient design can be achieved in real life operation. And that's the key point here. Okay, the figures I got from 2 scientific publications. So the left one, so it just a plot the performance gap for the different types of commercial buildings. And you can tell, so some of the prediction, the design prediction, they underestimate the real life energy use, but also there are some prediction they overestimate. So that's the story for the commercial buildings. Then another figure, so this one, it is also a comparison between the simulation and the real life performance, but it is the data for the commercial buildings. And we deliver the similar message here. So for example, there are different types of the end use. For example, the heating. So the real life, the energy consumption is almost 40% higher than the simulation. But the story can be different for another end use. For example, I can use the cooling here. So the prediction overestimate the real life consumption by nearly 30%. But one thing I want to clarify, so this data, they are the data collected from the traditional buildings. So they are not the high performance energy efficient buildings we are talking about today. Compared to those traditional buildings, the energy efficient building, they have much more rigorous requirement in terms, not just about the design, but also the construction and operation. And my question here is, okay, then in this case, does this performance gap issue also happens to energy efficient buildings? So to address this question, that's why we carry out a case study using a certified passive house as the case study. Okay, the passive house. So very often people think the passive house is just another name for the super insulated house with no heating and cooling. But that's a little bit a misunderstanding of the passive house. By definition, the passive house is a concept paramount the thermal comfort with low heating or cooling energy. And the Passive House Institute, they also offer a set of numbers to assess if a building can be classified as a passive house or not. So of course, the first criteria, it is about the thermal comfort. So the overheating frequency should be no more than 10% of the total occupied hours. And also there are 3 different criteria for the energy use. For heating and cooling, the maximum is 15. The PER, you can think it is very similar to the total energy consumption. However, it is in a context of a future scenario. So the future scenario means the energy, all the energy is supplied for the renewable energy source. And the threshold here is not a fixed value because it depends on the on-site renewable energy generation. And in our case study, because we have a rooftop PV system, and based on the generation, so we can determine the PER threshold. In this study, it is the 73. And the last criteria is the air tightness. So it is to control unintended air leakage through the building envelope. And the threshold is no more than 0.6 air change rate. Okay, so what I have here is to give you a quick description of the case study building. As I said, so it is a certified passive house. It is used for student accommodation on campus. And we have 6 stories, and it contains 115 studios. It also has multiple communal space for kitchen, laundry, and also entertainment facilities. And we have a good level of the building insulation. So the building is constructed by the CLT concrete, insulated by the rock wool, and also the rigid panel. Probably, yeah, there are a little bit more downstairs. But anyway, we have a good insulation. And also the heat recovery ventilation system. So this system provides the fresh air to the indoor space. But during the winter time, so there's a thermal battery inside of this ventilation system, heat recovery system. The thermal battery will preheat the cold outside air before supplying into the indoor space. And also the thermal battery, it connects to this heat pump. So it is the heat pump water heater system. And the seasonal COP, the coefficient of performance is around 2.5. And you can see, so we have active heating system, but we don't have active cooling system. So the students, they rely on the natural ventilation for the cooling. So that's a quick description about the building. Because we need to assess what's the discrepancy between design prediction and real life performance, then the first question is, so what's the prediction model? The prediction model we use is this package, the PHPP. So the PHPP is the only authorized software in Australia for passive house certification. And this simulation apply, I know it's a little bit terminology here, so, but I'm going to elaborate a little bit further later. So it is quasi-steady state method to predict not just the energy, but also the thermal comfort. And interesting about this simulation, it is the computing environment. Actually, it is a spreadsheet, but it contains a lot of connected worksheet. So here I just show you the flow chart of those different worksheets. So in general, there are 3 classifications. One for heating calculations, another for cooling calculations. It also contains the thermal comfort assessment. And the last one, it is for the PER. I just want to clarify, okay, the PER is not just about the heating and the cooling. It is as Tuan said, it is whole of the home, whole of the house. So it also contains the domestic hot water system, the lighting, the electric appliance, and so on. Okay, in terms of the measurement data, So we get the metered energy from building management system. So it contains different end use, including the ventilation, heating, lighting, and so on. And we also installed wireless sensing network for indoor environmental quality monitoring. So the power of this data, of course, we can assess the thermal comfort of the building occupants. We can also apply this data to assess the other indicators associated with the health and the well-being of the people. Okay, so a big table here. So it tabulates the measurement values and also the design prediction. The design prediction, so there's no problem to meet the threshold because we will already get the certification. So however, the real life performance is not as good as we predicted, as we designed. So you can tell, so the simulation, it is over optimistic in terms of the thermal comfort, the total energy consumption, and also the air tightness. On the other hand, the simulation, it is too conservative in terms of predicting the heating demand. So you can tell there's a significant gap. And also the figure here, it is for the PER. So this figure divided the PER into, I think, 8 classifications, depending according to the different building service functions. And we can tell from the figure, the gap in PER is mainly due to the underestimation of, so the blue part, it is the ventilation. So a little bit gray, the brown color, so it is the underestimation of the lighting. And also the green one, so it is underestimation of the plug load. Okay, so I just show you, so the magnitude of the performance gap. Then the next question I want to address, so what's the underlying causes? Actually, there's a lot of the reasons, and some studies, they classify those reasons and map them into a building's life cycle. But today, my interest is to look into the uncertainty associated with the modeling. More specifically, it is the limitation of the simulation core, the quasi-steady state method. And another one, it is the assumption, the inaccurate assumption made for the profile used in the PHPP. Okay, yes, we are engineers. We are serious about the numbers and the equations, but I don't want to bore you with those equations. I just want to say, okay, this approach is based on this ISO document, but I really want to highlight the two key assumptions underpin this approach. The first assumption is to aggregate the different layers of the building elements into one single layer. So this is to simplify the heat balance simulation. Another key assumption, it is to use a correction factor. So those are the correction factor to simplify the dynamic behavior of the building. So these two simplification, on the good side, we can save a lot of computing power. So that's why we can run the simulation in a commonly used spreadsheet. On the other hand, it also introduced certain level of uncertainty, and that's why we can observe the performance gap here. Okay, also a busy slide here, but what I do here is try to compare the so-called the PHPP profile with other profile. So the profile, I show here. So it is the plug load and also the lighting density. And you can tell from the figure. So in PHPP, the profile remain the same across 24 hours in a day. And obviously, it is not the way we use our building. And here I also plot the profile used in NCC. And we can see some variations. So there are peaks during the morning and the evening hours. Yes, this can represent to a certain level the way how we use our homes. But because this is a university building, so the university, the campus, they have their own dynamics. So that's why we use a lot of the monitoring data, actually 2-year data, to develop the data-driven profile. So 1 year data to generate the profile and another year for the validation. And you can tell we reveal a quite unique pattern. So we have 2 sets of the profile, 1 set for the teaching period and another set for the non-teaching period. So that's the mindset to match the way how we run the campus. Okay, so I just quickly go through, so what's the limitations? What's the underlying causes? Then how can we narrow the gap? The approach we took is to introduce extra worksheet into the PHPP computing environment. And those extra worksheet is to enable the bottom-up dynamic approach, and also adding a bit more profile that can better represent our real life. And we enable the dynamic approach through solving 18 by 18 matrix equation. So if you would like to know more about it and you have the interest about the numbers, then you can go for this ISO document. But today, probably I just skip it. Okay, so the interesting is here. So we have a lot of diagrams here. So this diagram, they provide a good visualization of the performance gap across 12 months in a year. And it is the comparison in terms of the thermal comfort. So these 2, they are the PER, that you can consider it as a total energy consumption. And these 2, they are for the heating. So the 3 on the top, so they are comparison between the measurement, the measured value with the prediction from the PHPP. And the 3 on the bottom, it is also comparison between the design and the real life operation. But the design, the prediction is based on the PHPP model we improved. And you can clearly tell, so if we implement the dynamic approach and introduce the data-driven profile into the PHPP, then the prediction, they show a very good alignment with the with the black. So the black one, they are the measurement data. So that's perfect. And of course, we also introduce, a few stats to measure the uncertainty of this model. And we also compare with the industry guideline, and we fulfill all the requirements. Okay, I just want to wrap up my talk by a short summary. First of all, if we want to claim the energy efficiency, claim the carbon reduction from energy efficient buildings, we need to bridge the gap between the design and the real life performance. And the performance gap issue, it also happens to the energy efficient buildings. So we demonstrate this problem using the passive house study. And there are many reasons for the gap. So the 2 limitations I discussed here is the limitation of the simulation core itself, and another gap is the assumptions embedded in the PHPP. And also we demonstrate a cost-effective approach to make the changes, the little changes to the simulation model and to reduce the gap. And the one thing we would like to move forward is to develop the feedback mechanism between the performance data or the post-occupancy evaluation data with different phases of a building's life cycle. So the illustration here is to show you the potential benefit of this feedback mechanism. For example, with a good understanding of the performance gap, then we can improve our future design by modify those problematic assumptions made in the simulation. And also, if we get a large amount of the data, and those data can help the policymaker to define a evidence-based performance target, and can also inform what will be the upgrade for the next legislation framework. And another thing, the beauty about the feedback mechanism, it can support identification of the best practice in building operation and also prioritize the retrofit options. So we can achieve not just the design excellence, but also the operational excellence. Okay, that's all from me today, and I'm happy to take any questions. Thank you.
Thank you very much,
Thank
Jenny.
you.
I think that's a great presentation.
So-
I think there's a big gap we can see between the measured data and with the
Yeah.
simulation.
Mhm.
Highlighted all the thing we need to do to work on the software side. But I think we can take one question, but I think if any burning question, otherwise we can give the question to a PA. Yeah.
I have a question. I think I know the answer, but have you done the same thing with NatHERS?
NatHERS, we have an ongoing study with CSIRO. So we are currently have different experimental campaign in different states. We will going to monitor the real life performance from different houses. And I hope I have the chance to share the result maybe in future meetings.